All right. Good morning, everyone. So, thank you for coming to my talk. That shouldn't have worked. Payload Development 101. There's a little bio of me. That's me in a different shirt. There's a few things about me if you want to write a biography or something like that. Anyway, so let's get to the who and the why of where this talk came from. So I wanted to put this talk out there first and foremost for the red teamers out there that are coming up and having to learn about how to take this off-the-shelf malware like Cobalt Strike, Metasploit, those kinds of things, and get them up and running. But I also want to call out the blue teamers. So during a lot of our debrief calls, we get asked, okay, you guys are coming in year after year. You're able to get around our EDR at least at some point. What can we be doing in the off season to kind of prepare for these kinds of things going forward? And kind of gave me the idea that maybe I need to put some of this information out there so at least if the blue teamers do start researching this thing and start using the same tools that we use, you can actually start figuring out where your EDR or other security products are breaking down. And I wanted to throw a quote in here from Jeff McJunkin, if any of you guys know him. Everything's stealthy until they're watching for it. So a lot of these things can be applied, but it's also very much something that if you're not watching for it at all, there are no alerts. So payload development is definitely a cat and mouse game. I have definitely had payloads that were working on Friday. I've got beacons all over the place. Everything's going great. I come in on Monday, and it has completely been shut down, and I cannot get back up and running without alerting the blue team. So just remember that you may have these things working, but they may stop working at any time. Another thing is keep it simple. I have had tests where I have thrown absolutely everything at it just to turn around and run a PowerShell script and absolutely get a beacon up and running. So just make sure that you're checking off all the simple stuff first. Every environment is definitely different. I have tested a lot of different EDR products, and I've even had back-to-back tests where both clients had the exact same product. In one case, it's like it wasn't even there. The next week I go in, feeling a little confident, and then, absolutely get owned. So, it all depends, too, on how that security product is being tuned. But to be clear, as far as this goes, nothing here is new or groundbreaking. It's definitely something that your team may be able to use, but it is also, everything here is out there in the public domain. So I wanted to include this too to give credit where credit's due. You've got your researchers, you've got your open source tool writers, those are the real heroes. I'm just running around down here at the bottom acting like I know what I'm doing. So, just to kind of run through a quick roadmap of what we're going to look at here, I want to talk through some of the initial considerations. This is just the very basic stuff of what we consider when we're writing a shellcode loader. Then we're going to talk about just some of the initial protections that are present on a lot of Windows machines. That's what most of this malware is going to be targeting. We'll start talking about the sandbox and how that plays into execution of your payload. And then we'll talk about static detections. These are the things that when that file is sitting on disk, what are some of the indicators that are going to get it caught? And then I'll run through a few of the most common execution methods that we use. And then the very last, we'll have some slides that have some resources for training and for learning more about these topics. So let's go through some of the initial considerations. The column over here on the left, those are the most common languages we use. VBA not as much now, but once you're in, you can still use it. But the C and C++, it's obviously a mainstay. All of your .NET code, we've been delving more and more into the F#, but with C# and PowerShell, we still use that quite a bit. Now we have had to go off the reservation a little bit and use Rust, Golang, Nim, Python. But in a lot of cases, we're not using those as regularly, so we usually stick to the stuff on the left, but these are a lot of options for common tooling out there. This is a whole laundry list of file types that we use. Normally we kind of start at the top and work our way down, but it really depends on the context of the situation, like what is going to work for the environment. And in a lot of cases, we'll start throwing stuff like the click once applications at an environment, and the client had no idea that that was even a thing. They've never actually used one of those. So, sometimes, again, kind of if they're not aware of it, it could just fly completely under the radar. We have had situations where just one of these file types was not common, so it just worked. So another thing, and this is a very important part that we try to stress when we're saying that you do need to consider during payload development, is you want to simulate delivery. Nobody's ever going to develop malware in your environment and then just run it, at least not at first. So you want to simulate how an attacker is going to get initial access. So you want to download it through a few different things. You can try browsers, PowerShell, BitsAdmin, curl. You can also write like a download cradle in C# or F#. But you want to make sure that you run through these as well if you're testing within your own environment, because you want to make sure that it's, simulating as closely as possible the zone identifiers that get attached to every file that gets downloaded. So the zone identifier, it's also called mark of the web. This is an alternate data stream that gets attached to every file that's downloaded on your system. And that's how Windows knows that you downloaded this from the internet. That's how Smart Screen works. That's how a lot of the protections that go into play here, they're looking at that alternate data stream to see where it came from so that they can determine whether this is something that needs more scrutiny or not. So the last line there is actually a PowerShell command that will show you the alternate data stream. And here in a couple slides, I'll kind of show you what that looks like. So some bypasses for the zone identifier we very commonly use droppers. This would be like a base64 encoded file in an HTML file, like HTML smuggling, which can get into its own thing with the mark of the web, but there are ways around that. You can also encrypt the file with AES, but each of these things have their own indicators, which can lead to more scrutiny as well. Hey, thank you. But we also like to use container files. Now, zip files, it's getting harder and harder to use a zip file where it doesn't attach the zone identifier. But there are still some third-party zip programs that do not attach the zone identifier when it's extracted. Also, tar archives. This is a part of Windows now. There is a Microsoft version of tar. The only problem with this one is the target can't just double-click it like a normal zip file and extract the files. They have to run the tar command to pull it out. But there is no mark of the web attached, as we'll see on the next slide. You can also try throwing it in like a virtual hard disk. This would be like a VMware or VirtualBox hard disk file. But they have to be administrator to be able to mount those files. So you would have to be targeting someone who has administrative access on their machine. And then we used to use ISO files a lot. By default, low privilege users can mount an ISO file just by double clicking on it. And all the files within, while the ISO file would have the mark of the web, the files within would not. So Microsoft has since fixed that. That's why I threw the deprecated tag on there. But these are just some ways to get around the zone identifiers or the mark of the web. So at the top here, I took and just made a simple Python-to-exe program, threw it up on a droplet on the internet, downloaded it, and as you can see, this is the alternate data stream right here, where it shows that it came from the internet, and it shows the name, the original name of the file when it was downloaded as well. So you can't just change the name of the file to try and get around that. But as you can see down here at the bottom, you can tar the file. I took the exact same file, threw it in a tar file, threw it on the exact same droplet, downloaded it, extracted it, and as you can see, there is no zone identifier there. So this is what we're aiming for, at least if we're trying to get past mark of the web. So now that we've kind of talked about some of the initial considerations, let's talk about some of the defenses that are going to be there. So at a very high level, the anti-malware scanning interface, or AMSI, is basically Windows Defender's antivirus. This gets injected into every process through the AMSI.dll, and this is what Defender is using to look for signatures of malicious files. Since it's loaded in user land, it can be bypassed because you have full control over everything that gets loaded into your process. But, you know, Microsoft is wise to that, so they're also signaturing the bypasses, which is, you know, again, back to the cat and mouse game. So some of the bypasses that we very commonly use, there are tools like Defender Check and Threat Check where you can go through and figure out exactly what Defender is flagging on, and then just change those strings or that bit of data within your program. Another thing is, so AMSI has a scan buffer where it reads the file in, and that's how it goes through and parses for the suspicious strings. But you can actually just set that scan buffer to 0 bytes, and it'll think everything's great. So what it'll do is by patching that to 0, now every file that gets scanned within that process, it can't fit in the buffer, so it just assumes that it's good. You can also patch the function for the initialization, the AMSI init failed, and you can tell the process that AMSI just didn't load and just to continue on. And it's actually a very simple patch to throw in there. Another thing we look for is the availability of tools that came out before AMSI, like PowerShell version 2. If that's available on a system, then there is no AMSI integration, so we don't even have to bypass it at that point. But if you want to try looking up some at least PowerShell versions of the AMSI bypasses, you can go to amsi.fail. This will give you a randomized AMSI bypass in PowerShell, and every time you load the page, you get a new one. So Microsoft got wise to the fact that people were bypassing AMSI, so they implemented ETW. This is event tracing for Windows. A lot of EDR products often use this as well, and they'll create their own custom consumers. But what ETW is actually doing is it's correlating event logs so that you can create suspicious behaviors based on a series of events versus just one event. And by using that, you can kind of hone in on things that may have flown under the radar as far as antivirus goes, but it's definitely sticking out like a sore thumb for being malicious. All of the API calls for ETW are contained within ntdll.dll, which is another that gets loaded into every process. So this can be bypassed as well, but again, tampering with it can be detected. So some of the common ways that we get around ETW, especially in .NET tooling, since .NET is an interpreted language, all of the things within your .NET tooling can be parsed. So we go through and just change known strings. What's crazy is things like literally changing the name of Mimikatz to Mimidogs has been enough to bypass things in the past. Change the signatured namespaces. So Rubius is a very common Kerberos tool that we use. If you just change the names of some of these things, that's usually enough to get around it. Also, the tools that you download from GitHub, especially the .NET tooling, they have metadata attached with a default title, product ID, GUID, those kinds of things. You can literally just go in and change those to anything else, and a lot of times that's enough to get around the signature. You can also patch the API calls. So since some EDR products actually use ETW as their source for monitoring and for picking up on those event logs, just patching out those API calls can, or the call hooks rather, can be enough to start blinding the EDR. So we talked about hooks in the last slide. So let's explain what a hook actually is. So a lot of security products will place instructions at the beginning of an API call that they are interested in monitoring. So as you can see here, this is NTDLL. The NT read virtual memory, as you can see here, it doesn't do anything to set up the stack or anything like that. All it does is immediately jumps to another memory address. This is not how the stock NTDLL would work. So what it's doing here is it's actually jumping to a security product's DLL or some kind of other executable so that it can parse what's going on here. A normal call would be something like this, where it's moving a register value to the stack and then calling the function that needs to be called so that now it has its argument there. And that would be a normal API call in this case. So there are ways to unhook the API calls that get modified by your security products. You can actually just look through every API call in that DLL space and look for ones that start with a jump and then just overwrite it with stock bytes. So you would be overwriting it back with the bytes that would be from the legitimate NTDLL so that it no longer jumps to that security product for monitoring. You can also just load the entire DLL back into the process over the modified NTDLL or whichever DLL it is. And that way you've got a clean copy from disk and it overwrites every hook that was there. Now, Tylus, Matt Eidelberg over at Black Hills, he had a pretty cool method for loading the DLL. So a lot of security products actually watch for an application to load NTDLL a second time or kernel32.dll. So what his idea was to, as soon as your loader starts, it starts another process in a suspended state before the DLL can be overwritten with or patched by the security product. And now you've got a clean copy of NTDLL in memory that your process owns, so it just copies it out of that process space into yours, and now you've got a clean copy of whatever DLL had the hooks in it. But really, this is a chicken and the egg problem because all of these things can be detected, especially tampering with anything that would involve removing security products visibility into a process. So another response to this would be using syscalls. Now a syscall is basically a kernel level call. This would be as high a privilege as you can get, but users do have to be able to interact with kernel level APIs at times. So Microsoft's solution to that was to write API calls in NTDLL that are basically just filters to the kernel level call. But this gives security products and other mitigations the ability to kind of monitor what's going on there. But what we can do instead of calling the hooked functions is we can just set up the assembly, as you see down here, and just manually call it ourselves. Then there's not an actual call from our code to this call other than we are just manually doing what that filter call would be doing. This can be stealthier than user-land APIs, but again, this can also be detected very simply through no program is ever going to call a syscall without actually using the name of that filter API call. So if you want to generate syscalls to replace some of the suspicious API calls within your code, syswhispers was kind of the first, one of the first kind of easy to use tools to generate syscalls. The syswhispers 2 is only 64-bit. I think syswhispers 3 was where they implemented 32-bit as well. But you can also do it indirectly using the Sector 7 Hell's Gate or Halo's Gate. And what this uses is kind of a way of walking through the functions that are loaded and then indirectly figuring out where those syscalls live in memory and then setting up the stack and calling them for you manually. You can also do syscalls in unmanaged assembly code within C#. God help you if you go down that road. It is a very difficult thing to do correctly, but once you get the hang of it, it's not too bad. So now we've kind of talked about some of the initial protections. Let's talk about the sandbox. So what exactly is the sandbox? AV and EDR products are going to, a lot of times are going to execute files within a protected memory space just to watch for suspicious behavior before they allow the actual execution to continue. Most of the time this is from a small virtual machine that's either hosted locally or remotely. And the telltale signs can be determined programmatically prior to your payload detonation. So you can actually build code in, which we'll kind of talk about here in a minute, that can detect whether we're in a sandbox or whether this is a real user actually executing this process. So the first sandbox bypass that we very commonly use is time. So the name of the game is to slow down execution. Security products can't hinder a person, or excuse me, a worker from actually doing what they need to do. Otherwise, nobody's going to actually use that product. So what we can do is we can just delay execution by using things like the Windows APIs for sleep calls, so that we can get around the time limits that the EDR would use in the sandbox to determine if something's bad or not. Now, a lot of security products have gotten wise to this, so now they've figured out that they can just simulate the time difference, and it all happens immediately, and then the malware still executes. Also, they could be watching for sleep API calls that aren't commonly used by that kind of process, so that could also be a detection that would lead to further scrutiny. So the way we get around it, we usually code in things like calculating large prime numbers or calculating the Fibonacci sequence to a certain number. And what this does is it slows it down organically enough that we can get around that time constraint in the sandbox and manage to get our payload to execute. And yeah, as I said there at the beginning, you know, the EDR and other security products can't slow down the user experience or else no one's going to use it. So another bypass that we like to use is size. The name of the game is just be too big to fit in whatever you've got here. So where you would see this is like we might have malware that's only a couple kilobytes, but we can use tools like DigDug or Mangle to actually expand that out. So DigDug was written by a guy on our team, Mike Saunders, and what this does is it just takes English words and pads out the data section with very low entropy data, which is non-random data, at least to the machine, and this will make the binary very large. Now the problem with that is that does not compress very well, so you've got a huge malware file that you have to send into an environment. But again, Matt Eidelberg over at Black Hills wrote a tool called Mangle, and what this does is it just uses zeros to pad it out. The cool thing about that is you can pad it out to like 700 megabytes, and then when you zip it down, it actually just zips back down to the original file size. Now, a lot of security protection software will not scan large files because that takes time, and again, that goes back to you know, kind of ruining the user experience, so they have to kind of skip over certain things. Another one is just looking to see if the machine is domain joined. A lot of these sandbox virtual machines are not domain joined, especially if they're off in the cloud somewhere. So what we can do is we can just check and see simply, is this machine domain joined? If it's not, we just nope out or do something innocuous and move on with our day. Or we can also actually key it to the specific internal domain that we would be expecting to see. Now, the only problem with that is you would have to have some prior knowledge of what that internal domain name is, but it's not terribly hard to find if you know where to look. But the sandbox VMs are rarely ever going to pass this test, so we get legitimate execution instead of just being detected within the sandbox. So there's a whole host of different sandbox bypasses. Brandon Arvanaghi and Chris Trunzer made a GitHub repo in a bunch of different languages. I've kind of got them listed here. But they also break it down into detections around, is a real user sitting at this machine, or am I just on a real machine? So you could look at different things like monitor resolution, the amount of RAM, the MAC address, things like that. These are things that it's very easy to tell. You know, if this thing only has 1 core and 512 megabytes of RAM, obviously that's not someone, you know, using Office products and doing their day-to-day tasks. So we can just kind of nope out at that point. But if you want to look through here, the Check Please GitHub repo it's a gold mine for different ways to bypass the sandbox. So we've talked about all the way up to now, we might actually have to have our payload sit on disk for a little while. You know, this would be like if we're trying to use a service binary, or we actually have to load a DLL from disk. So we need to be able to have that sitting on disk without being detected. Most of the time we're trying to load position independent shellcode with our loaders. And this can be stored in variables that can be detected at rest. If there is a huge blob of just random data sitting in the data section of an executable, a lot of times that can be enough to at least make it suspicious, if not outright blocked. So when I talk about randomness, entropy is basically a synonym for that. It's looking at how random is the data that's sitting there. Does it look like it should be sitting there, or does it look like it was shoehorned in? And when you encrypt your shellcode or you encode it, this can also increase the entropy pretty significantly. So let's talk about how we can get around that. One common way is to actually encode everything as UUIDs, or unique identifiers. These are 32-character strings that also follow the same format of hexadecimal as our shellcode would. So by having these UUIDs, which are a common string format in executables, we can actually just encode our shellcode and walk right past any static detections. Also, if you just throw it in the end of an image files by their nature are very random data. So if you can embed your stuff in there and then programmatically pull it back out at execution, that's another way to get around just the entropy detections that would lead to suspicion. Another thing is to map the bytes to lower entropy data. So kind of like I talked about earlier, Mike Saunders on our team wrote a tool called Jargon. And what this will do is it'll take your shellcode and it'll map all possible 255 bytes to a dictionary word. So instead of having, hexadecimal 1, we would have the word cat. And then we would have a map of all these words so that at runtime we can basically decode it back to shellcode and then get up and running. Another way around this is just to use a different encryption key every time. If you use the same encryption key every time, the first few bytes are probably always going to be the same because the first few bytes of shellcode are typically the same. So if you use a different encryption key, that automatically at least lowers the rate of detection for encrypted shellcode. So another big tip, I learned this from the White Knight Labs guys, different compilers optimize code in different ways. So if you compile everything with Visual Studio, you're probably going to get the same product every single time. But if you just turn around and use the minimum new for Windows compiler, the MingW, it may just completely walk past any signatures that are out there for that file. Also, another big thing, and it's a lesson you have to learn sometimes the hard way, is if it came from GitHub, it is signatured. If it's out there, the security companies are looking at the exact same things that you're looking at, and they are writing signatures for a lot of that stuff out there. Also, if it's a widely used C2 framework, the default payloads are all signatured. They have access to software just like you do. So we use a lot of Cobalt Strike and a lot of Sliver. Covenant, not so much these days, but these products are very much signatured by the security vendors. So some ways to bypass these signatures, it kind of goes back to what we talked about earlier. Just change the variable names or lengths. So honestly, if it's always using like a 50 kilobyte buffer and it fills it with A's, just fill it with B's. That can be enough to walk right past a detection. Change the checksum or hash of the file. If you just echo an image file onto the end of your executable, that completely changes the checksum of the file. And then, like I said on the last slide, change the default encryption keys. In a lot of cases, if you can make the encryption keys just 1 byte longer, that can be enough to get around it. And then bypass some of the default C2 framework detections. So we use Cobalt Strike a lot. We've invested a lot in the kits that come with Cobalt Strike to modify as much of the default actions as we can. They've also created a compilation script to recompile all of your default code bases, and that can be enough just by running that recompilation thing to change all the base executables that get used. So it's nice to talk about the order of operations. So pretty much all the malware does the exact same thing. It provisions a memory space, it copies your shellcode into memory, it makes it executable, and it runs. So one thing we found that works pretty effectively is just break up the order with unnecessary code. So, have it provision the memory space and then calculate the Fibonacci sequence. Have it copy the payload into memory, and then literally just increment a variable 1,000,000 times for no reason. Just kind of throw spaghetti code, dead-end code in there, and that can be enough to kind of at least break up the order of operations enough to get around some of those ETW signatures. And then this is just kind of a laundry list of little things to think about. If your payload calls back out to a C2 server half a second as soon as after it executes, that can be enough to make it suspicious. The other thing to think about is in Windows, when you execute something, you are executing as the child of something else. When you double click an executable, you are executing as the child of Explorer.exe, which is your desktop environment. So it's good to think about and look at what does the parent-child process look like when you look at the processes in memory. I threw an example here. Why is Microsoft Word executing command.exe? Why is it executing PowerShell? It should never be doing these things, and that's an obvious indicator. Also, injecting into processes that shouldn't be talking to the internet is usually a dead giveaway. Notepads should never be talking to the internet. If you inject into something like a web browser or a chat app, then those are supposed to be talking to the internet, and it takes a little more nuance to figure out that something malicious is going on here. Also, memory protection. So if you are a programmer, you should not be setting every memory region as read, write, and execute. Nowadays, you set it as read, write, you write your stuff into it, then you change it to read, execute, and you execute from there. But if you're being lazy or if you just aren't aware, setting it as read, write, execute can be an indicator. So now that we've kind of talked about at least some of the base things that go into some of our shellcode loaders, let's talk about some of the most common execution methods. I know this seems obvious, but the portable executables, the EXEs, this is pretty much the most common way we execute. But there's a lot of different execution methods, and we'll talk about that on the next slide. It's easy to blend in just by changing the name or the location of that executable. However, it is highly scrutinized. So even my grandma knows you don't click on an executable, like that's been beat into everybody's head. So there's no reason that someone should be receiving a phishing email and running an executable unless they think it's legitimate. So just by, just the file type alone is enough to keep someone from double clicking your payload. Also, if application allow listing is enabled, then your application may just be outright blocked. Application allow listing is a feature in Windows where you can set an allow list of executables that are allowed to execute, but if it came from the internet or if it doesn't match a certain list, then they can just block it outright. But like I said, this is one of the most common file types that we execute. So some of the ways that we can execute an EXE is obviously cmd.exe. When we talk about the shortcut files as well, this is always going to be the most common way of execution if it comes from a shortcut file because it's going to run it as a child of cmd.exe. But you can also just pull up a command prompt and run it. You can do the same with PowerShell.exe, which does mostly the same thing, except now you're running as a child of that. But one of the cool things that I like to use is Explorer.exe. It has a flag that you can throw in there, the separate flag. And when you do this, what'll happen is it'll launch a second copy of Explorer.exe with your payload as a child of that. But then what it does is the second Explorer.exe just dies. It disappears. So now you've got this orphan process in memory, which is fine, but now there's no parent to tie it back to. So this can actually get you up and running where CMD or PowerShell may get you caught. Another file type that we use pretty commonly is MSI files, the Microsoft installer files. So when you run an MSI file, it can actually execute commands prior to or after the intended installation file. So in this case, you can have it do something completely legitimate, like try to install Zoom or WebEx or whatever, but you can also modify it so that it runs your command prior to that and gets your payload up and running. And especially if the MSI file is something that the user is expecting, we do very commonly get execution through that. I talked about the shortcut files, but the other is service binaries. So service binaries, when you install a program that launches at startup every time, these are usually installed as services. If you can drop that executable on disk in the place of that service or even create your own service, now you've got persistence as well, where your payload is going to continue to run until it's detected. So another big one that we use is MS Build. So MS Build is built into every copy of Windows 10 by default, and it's a .NET compiler. When you run Visual Studio against .NET code, MS Build is usually what's compiling that. So it's just as simple as formatting it into an XML inline task file. You can write just straight C# code within that file. And then as long as the XML is formatted correctly, just run it as an argument to MS Build and you get up and running. This is a big application allow list bypass because it is signed by Microsoft. So in a lot of cases, the application allow listing is set to, if it's signed by Microsoft, it's okay to run. And we very, very commonly get up and running with that. And the XML payload file can bypass static detections because it's just text. So as long as you're not being caught on like a suspicious string within your C# code, a lot of times these can just sit on disk without any issues. So another trick with MS Build is you can change the payload file extension from XML to CSPROJ or C# project file. And if you do that and it's in the same directory as the MS Build executable, it will actually just execute automatically. You don't have to pass it in as an argument. So where we would use something like this is we would copy msbuild.exe to, like, say, the startup folder or something that's going to be executed by another known application, and then set our CSPROJ right next to it. And now in the logs, there's no arguments. So we're getting persistence just based on the fact that MS Build is being executed, probably under a different name, and we're getting our payload up and running. You can also pull the C# code straight out of that XML and just put a reference to it in there, and then host your C# code on a WebDAV share out on the internet. Or you can just build in logic to actually parse it straight from a web page. And then this will load remotely your code and get you up and running. And because it's C#, you've got full access to all the Windows APIs, or, you know, if you're feeling adventurous, you can do some syscalls in there as well. But either way, this gives you full access to getting your code up and running. Another kind of similar technique is to use install util. So this is located in the same place. It's the .NET installation and uninstall utility. But again, it's on Windows 10 by default. Again, it's an application allow list bypass. And it can execute C# code, but you do have to compile it in DLL or executable form. So first, you're going to have to be able to drop that to disk without being detected, which is the static detections we talked about. And also, install util is not meant to run for more than a couple minutes. So if you have a long-running install util process that's been running for 2 weeks, that's probably an indicator of compromise and probably something that needs to be looked into. So again, this is the uninstall command, just literally passing the payload as an argument. There are some more flags you can throw in there to keep it from writing log files, but at its core, that's the easiest command there. One of the pretexts that we used to use before the ISO, you know, God rest its soul, had the mark of the web bypass, is we would take a Microsoft installer file for, say, like WebEx or Zoom. We just pull all the files out of it and then hide our DLL amongst that, and we would take the shortcut file that was set to start the installation of whatever that program was and just modify the shortcut file so that it had our install util command to run our DLL from the ISO file there. And then basically our pretext would just involve having having the user double click that shortcut and get up and running. So now this one is my favorite. This is something that I use almost on every test nowadays. So a proxy DLL, what it does is it takes a legitimate DLL, it exports all the same function names as a standard DLL, but what it also does is it allows you to kind of shim in code execution that happens at the same time. So what it'll do is, let's say you target version.dll, which is a very common DLL that gets loaded. You export all the same function names, you throw your code execution in there, but to keep the program from crashing, it actually still sends the request to the legitimate DLL. So this is a legitimate Microsoft function. And by using this, we can literally just throw a DLL beside something that it's looking for. You know, say it's looking for version.dll and it's not in the current directory. If we have write access to that, we can literally just throw our DLL down and the program will load without any issues while also giving us code execution. God, I still haven't updated that. So the name of the tool that we like to play around with is the Spartacus proxy DLL generator. I still don't know why I haven't fixed that. But basically, this will give you the ability to create proxy DLLs yourself. But the MSDN does have articles on how to write these proxy functions. So like I said on the last slide, basically, let's say we have write access to a service binary, but we do not have the ability to turn that service binary off. We can just download the service binary, see what DLLs it's searching for, and if all of them are not present in the directory with the service binary, we can just create our proxy DLL, throw it beside it, and now we've got execution in the same context as that service binary. We can also take legitimate Microsoft binaries and just set our proxy DLL right next to it, send that into an environment, and when the user double clicks on that legitimate binary, we get execution. So in conclusion, I wanted to kind of talk through a couple resources here. So a couple of blogs to call out. The 0xPat blog, he has a lot of code and demonstrations for why sandbox bypasses work. It's definitely worth a read, very technical, but very interesting. Also, the CocomelonC C blog, this guy takes any kind of shellcode loading techniques that he hears about and basically writes it up and gives C code that either explains it or demonstrates it. So definitely worth a look if you're looking into code samples for malware loading. So there are some paid courses. Sector 7, they're practically giving their stuff away. They only charge a couple $100 for each of their modules, like 6 or 7 of them. But they have some very interesting techniques that are pretty accessible and easy to learn with code samples. I haven't personally used it, but I've heard nothing but good things about the Malware Dev Academy. Those guys are putting out a lot of the same material, but they explain it in a lot of different ways. So definitely worth a look, and I think it's a one-time fee to get lifetime access. We have a course that we teach where it's red teaming from tip to tail, basically, and one of the parts is actually writing malware to get up and running in a simulated AD environment. The White Knight Labs guys, I mentioned them earlier, they usually teach their course. It's pretty awesome, and it's pretty cheap usually as well. And then 0 Point Security with the Red Team Ops course. Also a very cheap course and very accessible. The training material continuously gets updated, and you have lifetime access once you purchase the course. Some other resources, just some GitHub repos that I definitely wanted to call out. Donut can take any kind of .NET compiled code and turn it into like a shellcode file that you can then load into something else. UPX Packer is a really good obfuscation tool, but it has its own detections that are around it, and it can be detected that their techniques are being used. I mentioned Freeze earlier with pulling the clean DLLs out of a sacrificial process. Dark Armor is another good loader. So that one is at least worth a look in your environment if you want to try to obfuscate your tooling. this Protect My Tooling has a lot of interesting techniques, but if you want to see a ton of really cool red teaming tradecraft, definitely check out mgeeky's whole GitHub profile. There is a ton of stuff on there to check out. And then they've got the .NET Confuser EX. This is a .NET obfuscation tool that came out for legitimate reasons, but we use it all the time to get our tooling to run in environments. And then there's a paid option for obfuscating shellcode or generating a lot of tooling like macro docs and that kind of thing from Ballast Kit. This guy's been doing this for a long time, and he has some very interesting techniques that continue to help us be successful when we're trying to get up and running. So the takeaways, malware development is an entire field of its own. This is not something that by watching an hour-long talk you're going to completely understand, but if nothing else, this talk was kind of meant as a roadmap to kind of learn the concepts that are out there for what all is required to get around a lot of the protections nowadays. So, you know, you will have to do some self-study and research, but at the very least, I would hope that you would be able to at least understand the techniques that are being used. And understanding those techniques can help you understand where the gaps are in your security posture. So you know, you don't always have to go completely down the rabbit hole to understand this, but you'll at least understand what those tools out there are doing when they are bypassing your security products. So wanted to say, we got our own Discord if you're interested. If that's your kind of thing, I'm covers on there. We also do the Wednesday Offensive, which is a half hour every Wednesday where we have people from the security community come on. If you're interested in that, sign up. It's free. It's fun. It's not recorded. You're allowed to just throw questions at people. It's a lot of fun. And if you're interested in speaking on there, definitely reach out. And then this link at the bottom has the slides. It's a PDF of them. I promise you there's nothing malicious in it. That'd be a really crappy thing to do, especially as a security company. But you can get all these slides with clickable links in them to all of the tooling that I talked about. And with that, I'll open it up. Do you guys have any questions? All right. Well, hey, thanks for coming to my talk.